Introduce today's distinguished speaker, Professor Csaba Szepesvari from University of Alberta. He is a professor in the Department of Computing Science and also one of the PIs of the Alberta Innovate Center for Machine Learning. Before moving to Canada, Csaba was a senior researcher in the Computer and Automation Research Institute of the Hungarian Academy of Sciences, and he also had a variety of industry positions. Csaba's research is in machine learning, and more specifically is interested in reinforcement learning, online learning, and statistical learning theory. He is best known for UCT, an algorithm that led to a leap in the performance of planning and search algorithms for a variety of applications, but specifically for computer Go. Has authored 2 books, one on nonlinear approximate adaptive controllers and one short on reinforcement learning. And has also published extensively in most of the top machine learning venues. So he's also an editor of the Journal of Machine Learning and, associate editor, and the Journal of Machine Learning Research. So without further ado, I will pass the microphone to Csaba, and looking forward to hear how to make good decisions. Thank you.
Yeah, thank you, Christina. Thanks for the nice introduction. So I'd like to talk about learning to make better decisions. And as Christina said, I'm from the University of Alberta, Department of Computing Science, and this talk is based on most joint work with former student of mine, Yasin Abbas-Kori, and a postdoc of mine, David Pál. So with that, let's start. So being a computer scientist, you want to make a difference, right? That's the goal. So how are we going to make a difference in society? Some say that maybe we should build autonomous cars to save the lives of people dying on the road because of reckless drivers and whatnot. Autonomous cars would be much safer to have driving us around in the cities and beyond. Or you might think about that we should build voice user interface systems to make human-computer interaction more human-oriented, right? Less computer-oriented. And that's really a great idea. It can be very helpful. Doctors are actually a big crowd who are already using some advantages exploiting the advantages of such interfaces, but we could certainly do more. Or maybe we could save the lives of patients by building these intelligent strategies for treating the patients. So rather than one size fits all, you apply the same treatment to every single patient you meet. You should really look into the specific needs and characteristics of each of the patients, and you should tailor the treatment to them. Or maybe you should you want to build intelligent tutoring systems, bring education to the masses while improving it. So these are all great goals, and the question is, how are we going to get there? So how are we going to do this? So first of all, there are a bunch of things that help. So these days, there's a lot of talk about explosion of data. You can see the logos of all these companies that are popping up almost every day. And these companies have access to unprecedented amount of data. And maybe one common ingredient for building these systems that are going to make a difference is just make use of the available data. After all, there are huge amounts of them. So how are we going to take advantage of this? Well, the next ingredient is that, we're going to do a lot of computation. And lucky for us, computational power is still doubling every year and a half. So right now we're looking into parallelizing a lot of computation that we were doing. And with that, we can access more computing power, even on desktop machines equipped with a couple of GPUs than with the best supercomputer a couple of years back. So this is really great. This is amazing. It seems that we're going to make good progress if we just follow this. But of course, as Daniel Case-Moran wrote, you can have data without information, but you cannot have information without data. So we need something more to turn that data, after we have the data, into information, right? So it's not just about data. We need the algorithms that actually do process the data and turn it into information that's actionable. So how are we going to do that? So if you read the news is full of, deep learning results, improvements of state-of-the-art results on various fronts of machine learning, and all kind of prediction problems are being kind of solved or attacked, and these learning machines achieve unprecedented accuracy on various tasks. So a lot of people jumped on it, and it seems that we are making fast progress. So where are we exactly? So one example of recent advances comes from this large-scale visual recognition challenge, ImageNet it's called, ELSVRC. That's been running since a couple of years ago. So this is a very, very challenging task for computer vision algorithms. You have over almost 1,500,000 images, and you have 1,000 object classes, and the task of the machine is to look at one image and tell on the image what you see on the image. So you, in one of the tasks, you have to produce these bounding boxes, and you have to label the bounding boxes on what they are showing, and there are 1,000 different object categories. So it's a very, very challenging. It's not a small scale task. It's a very challenging task. And so one usual or one customer way of evaluating these machines that is used in this challenge or competition is that the machine is going to make a bunch of predictions. It's going to produce usually a ranked list of object categories. So there are multiple versions of this challenge. In one version, you just have to guess what's on the image. And they take the output of the machine, and they take the top 5 of the ranked items. And if among those top 5, you actually find something that's actually known to be an image, then you get that image correct. And otherwise, it's an incorrect guess. So still, like you might say that, well, this is very, very nice 2D algorithms that you're going to count something like this as correct, even if you have just one of the labels correct. But you have to take into account that this is a very challenging task. Even the human labelers who are labeling the image might not actually notice some things that sometimes the computers are going to notice. So in any case, the community decided that this is a good way of evaluating progress on this challenging task. And so they do this for 100,000 images that are held out, and they report the average error measured this way. And so if you look at what was happening over the years, since 2010, when this challenge was introduced, you can see that the progress has been tremendous. So overall, there is 1.7 times reduction in classification error just very recently. So you would think that like when you start there, you make some progress, then maybe soon we are going to stop seeing this progress. But actually, it seems that it didn't stop. And so about this accuracy, someone take the effort and try to compare it to the performance of human labelers. And they found that the differences are tiny. So of course, they found that machines make errors on different type of errors than the human labelers. So there is still room for improvement, but this is already pretty close to what a human labeler would achieve on this task under identical conditions. And then of course, well, there is no stopping. So this is just from my Facebook page from yesterday. Andrew Yang posted that, well, their newest algorithms even beat the GoogleNet, which was the winner of last year's competition. And so the war goes on. Great. So that's vision. And you might think that like once we are done with this humongous task, this very difficult task, vision is done. So let's look at some other domains. And another domain where there was tremendous progress is speech recognition. And the significant players these years are Google, Apple, Baidu, and they improve error rates constantly since the introduction of these new methods that process more data than ever before. And the error rates are constantly dropping, and some people are talking about the era of speech 2.0. So the question is, are we done? So yeah, so you could say that we can build machines that can process visual information if you want. We have an eye, and we can also build machines that have ears, and that's pretty good. But I would argue that this is great progress. Working with rich perceptual information is crucially important to advance the field. But at the same time, you need to make decisions. So I didn't draw the legs and the limbs, but you have to make decisions and you have to decide about your actions. So I would argue that maybe what is missing from this previous set of achievements is the piece when you make decisions and you work on the information that you collected and the predictions. So how are we going to do this? And of course, being a machine learning person, the answer must be that you have to use data, right? So reinforcement learning is the field where people think about building these machines, or brains, rather, that make observations about the world in a continuous stream and take actions and observe some reward, and they try to act in such a way so as to maximize the total reward collected. And the idea would be that by collecting a lot of data, then you're gradually improving your decision-making capabilities. Right, so the question is, do we have this? And there you go. Google DeepMind enters the picture. This is when reinforcement learning met deep learning and big data. This was happening during the last couple of years. I don't know, some people might have heard about this news. So this company was set up to crack AI, and their approach is to use RL and big data and maybe deep learning and other tools to achieve this. So how far did they get? So they have pretty impressive results. So one of the domains that they've been working on is computer games, more specifically the Atari 2600 games from 30 years before or more. So there is an awesome game simulator environment, and the challenge here is to build a machine that, while interacting with these games, learns to play in these games without any human intervention. And the requirement is that it should be the same learning algorithm with the same settings that works across many different domains. And here I'm just showing a few simple domains. And these results are, by the way, of our 2013 results. And just this SNPs, they made new announcements about even better results. But anyways, so what happens is that if you put together RL and deep learning and big data, what they are seeing is that a single algorithm is able to beat all previous algorithms. And in many cases, it came very close to the human level performance. In some cases, it's not. But right now, they have a much fuller understanding. This was just for a small set of games. They have a much better understanding of how far they can go. But anyways, if you watch the videos that they have produced, it's kind of amazing that there is a single algorithm that is able to play learn to play games in many different environments. What's important to emphasize here is that there is no feature engineering, nothing going into this. These algorithms look at the screen of the computer games. And the only information they get is whether they are making progress. And they use the same kind of actions as the humans would use. It's basically an abstraction of the joystick and the firing buttons and so on and so forth. So it's a multi-dimensional action space, and the computer is just looking at the images, the video flow if you want, and it gets this reward. So it's really in this reinforcement learning framework, and it keeps learning and learning and learning. And what I find is that single algorithm is able to deal with a wide variety of games, and it performs really well in these games. It's not just like it would be able to play a little bit. Many times its performance surpasses the best human player's performance. So when this happens, you know what happens next, right? So everyone's crying out. It's the doomsday, like it's here. AI is going to crash humanity. They're calling for action. And so this is from 12th of January, a couple of days before, from CNET. This is the headline, one of the headline articles. Artificial intelligence experts sign open letter to protect mankind from machines. So being responsible, I totally agree with that. The question whether we are close to this or not, that's an entirely different question, right? So, and this is the question that I'd like to ask and investigate a little bit next. So the question is whether if you put together all these awesome technologies, the perception and this decision-making technology, are we there yet? Okay, so is there anything missing from the big puzzle? So you might suspect, if you read the abstract of the talk, that I'm going to say that yes. Maybe there are some things that are going to prevent us if we just go down on this road and we don't do anything else. It's going to prevent us from scaling up to more challenging tasks, this set of technologies. So my main theme for today is data collection. How are we collecting data so that we can make good decisions? Are the ways we're collecting data is good enough, or do we need to improve? Okay, so to get you started on this, let's take a swimming lesson. All right? So imagine that you are a swimmer, and you're swimming in this river, and there is a current going one way. Okay? And you don't know, but at the one end of the river, actually down the river, if you get there, then there is going to be some reward. It's a humble pie. Okay? But if you would be striving to swim strongly against the current, then you would get to this big bounty. You would get a much bigger reward. So if you want to put this to numerical values, then maybe this is a reward of 1, and this is a reward of thousands, right? So okay, we have this problem. So I'd like to investigate a little bit this problem of what is happening to the algorithms that we all know and love in this setting. And to be able to talk about this, let's abstract the problem a little bit. So we're going to talk about a finite set of states. This is one state where you would get the humble pie, and this state is when you would get the big bounty. And you have 2 actions that you can take in every state. One action would just go downstream to the next state, and the other action would try to go upstream. But there you have a much harder job to swim against the current. So the probability, if you take that action of staying at the current state, is let's say 1/2, and the probability going up is also 1/2. All right, so you have this problem. So what happens if you just do what seemed to be happening in the past, that you just do this reckless data collection? Let's say you're choosing actions uniformly at random. The question is, how long do you have to wait before you're going to see the big bounty? Can you guess? Let's say I say that the number of states is in the range of 10 or 20. So let's say it's 10 for the sake of specificity. So give me some numbers. Like how long do you have to wait until you see the big bounty? If you start, let's say, in the middle, Some guesses. Don't count, just guess. It's 1 million? All right, good guessing. It's not guessing, I guess. So the question is, all right, fine. Sure, like if you have a state space of size 10, it's 1 million, that's already a pretty big number. What happens if we scale the number of states? Well, this is what's happening. Okay, so this is the time before the bounty is found. And this is the number of states. So you can see, well, for 10, it's not so bad, actually. It's not 1 million. But you would be right if you would guess 1 million, because this is 2 million. When you get to around 20, it's actually way over that. So what you see is obviously an exponential growth. So if you do the data collection at random, it's just a Markov chain that you were in. So it's computing heating times. It's nothing really fancy. Then you can compute these heating times, and you will see that you need exponentially many time steps before you're going to see the big bounty. And on the other hand, what's more interesting perhaps in this setting especially is that if you use the swimming policy that tries to swim against the currents, right? Then that policy, every time step, maybe it's not going to make much of progress, but at least it stays in place. So you can see that linear time is going to be sufficient for the swimming policy. And so you can see on this logarithmic scale graph that the swimming policy is making progress. It's hard to see that this is linear, but actually that's linear. So on this very, very simple example, what you see is that there is an exponential gap between a simple, uniform, random data collection policy and another policy that would try to do something. But of course, the policy that I chose, the swing policy, was the one that was going exactly into the right direction. So in a general learning setting, you will know which direction to go into. So it's a little bit less clear whether you can improve upon this otherwise pretty sad situation. So you can see this exponential gap, and then that raises the question of like how big is big enough, right? So we're talking about big data, but imagine state spaces which are like exponentially larger, even infinite, and you can totally imagine that well, no beta will ever cut it unless you're smart about how you're collecting your data. Okay. So let's change the game. So we're going to allow a policy to collect the data. And the question is going to be, can we design clever algorithms that steer the data collection in such a way that they get to the bounty, they discover the bounty in time less than exponential in the number of states. So what's the standard RL approach, by the way? So in RL, people being around, they have been aware of the problem that you have to like strive towards discovering the bounty, of course. But the standard RL approach, by the way, which is also used by these DeepMind algorithms, is the following. It's very simple. You just repeat the following. You learn a good policy based on the data that you have, and then you add randomness to introduce some exploration, because people figure that if you just follow greedily the policy that you learned, that you might get stuck in local Optimus, you have to explore a little bit. They add exploration. You collect some data across maybe multiple episodes, and this is what you repeat. So the standard algorithms that fall into this category would be epsilon greedy or textbook algorithms and Boltzmann exploration. More generally, I call this dithering. So you just induce some randomness, and otherwise you follow what you think is the best. So what happens to this dithering in the reversing problem? Well, what is the policy that's initially being learned? Well, you can imagine, right? So you take, let's say, random actions. You go down the stream. You get to the humble pi, so you see that, well, that's not so bad. So you start in the middle, so you learn that it's you're at least getting there something, a reward. So you go to you swim towards the humble pi. And then, okay, you add some randomness to that. So occasionally you are going to try to swim against the current, but it's going to be way worse than uniform random at the beginning. So once you learn something, you will have no chance, absolutely zero chance of ever finding the bounty, right? It's going to be way worse than uniform random exploration of the two actions, because right now you have a bias towards going to the humble pi. It's totally misleading you. This is not very smart, right? It's going to take more time. So tethering is not going to cut it. We need smarter methods. So before we can talk about what do we mean by these smarter methods, we have to talk about how we are going to avoid these methods. So there are two ways. So we can talk about how much data do we need to find a good policy. And these are the pure exploration problems. I'm not going to talk about this problem today. But it's an interesting class of problems. It relates to optimization, active learning, and it's very interesting. What I'm going to talk about today is when you evaluate the learning algorithm by how much reward it's collected along the way, because maybe it's more realistic, closer to the real applications. In real applications, even during the data collection, it's really hard to convince people that they should give up reward just to get something better. So altogether, this is the problem that I'm going to look into. And one side note here is that these methods require pretty different solutions, or these problems require pretty different solutions. All right, so this, in the second case, how we measure performance is called the regret. And the regret is simply the total reward that you collected from the beginning of learning compared to the total reward that you could have collected had you known something else, like had you knew, let's say, the optimal policy. That's pretty common to compare to that. It's a pretty harsh criterion if you ask me occasionally. This is the problem that we're going to look into, and I call it the exploitation problem, as opposed to the other problem. Okay, so I'm going to talk about two algorithms very briefly, and then about some results concerning these two algorithms, or two algorithm families, I should say. So two ideas. So one of the ideas is optimism in the face of uncertainty, and this goes back to the seminal work of Loy and Robbins, who worked out the bandit case. So it's a simplified reinforcement learning problem. You don't really have any states, you just have actions. And every time step you find yourself in the same state. And right, so what is the algorithm, or what is the idea? So you repeat the following. So given what you have observed so far, you can find the set of likely words. So you have the class of all possible words, and within that you find a set of likely words. It's kind of like an elimination that you can do. Like you see that, I was doing this, so it's not possible that, so I was walking that way, it's not, and I was able to do that. It's not possible that there is an obstacle between this point and that point. So you can rule out that word. So you do this elimination, okay? So then you have the set of remaining words that are still plausible. So next, what you're going to do is that you're going to find the best possible of the remaining words. Okay, so you have some performance criterion. You want to collect the maximum average reward, let's say, maximum bound. And you find the best possible word. So that's your best possible word. Of course, finding the best possible word might be very challenging computational problem, but you're topping that by finding the best policy in this best possible word. So it's really a joint optimization that you have to solve over the words and the policies, all right? But once you're done with this, you're almost done with the whole algorithm. And once you find this policy, you're just going to use this policy for a while. It's pretty important that you're not switching off from the policy right away. You can construct examples where that would lead to kind of like starvation. So you use this policy for a while until your set shrinks in a significant way, right? So until you can eliminate many more, like then you gain the information, and then you're safe to switch policies. And then you repeat the whole procedure. So this is called optimism in the face of uncertainty. Why is it optimism? It's optimism because you take the best of possible words and you just act in that word as if that was the true word. Okay? And I can also recommend this strategy for your real-world decisions, except that maybe you can't repeat many episodes of it too often. So maybe take it with a grain of salt. But it's a really good strategy. So how good it is, actually. So let's take a simplified setting when you have finitely many states and finitely many actions, and the rewards are in between 0 and 1. So for these problems, if you instantiate this algorithm template, then you get this algorithm that's called UCRL, Upper Confidence Reinforcement Learning version 2. It's an improvement of the previous algorithm. And so in order to be able to tell you how well this is going to work, we need to define what's the diameter of a word. So you have the states and you have the actions, and you can make the stochastic transitions, you can collect the rewards. So what's the diameter? So the diameter of a possible such word is the maximum of the best travel times between pairs of states. You pick one state, you pick another state, you ask, what's the fastest way of getting me from this state to the others using the actions? You find that, and you take the worst combination of these two states. So that's the diameter. For the reverse spin problem, the diameter is simply the number of states. Okay? And then you can show, actually, this is the work of Jaksch, Ortner, and Auer from 2010, that the regret of this learner is going to be scaling this polynomially with the size of the state and action space and the diameter, and scales with root t. T is the number of time steps that the agent was learning. So if the regret doesn't grow fast, if it's sublinear, then that means that on average, on a single time step, you're making fewer and fewer mistakes. You're converging to optimality. So if you see a suboptimal regret expression, that's learning. That's great. And then at the same time, to answer like how good this algorithm is, you can prove that this is almost optimal, near optimal, up to some gap in terms of the diameter and the number of states. No algorithm could do any better than this algorithm. So it's a pretty good algorithm. Okay, so this also answers our puzzle about the reverse spin problem. So in the reverse spin problem, this tells us that this guy, on the average, is going to be near optimal pretty fast. It's polynomial in the size of the problem, because in the reverse spin problem, the diameter is finite. But if you have a problem with infinite diameter, then you are out of luck, it seems. You shouldn't hope much there. Okay, so I'd also like to talk about a second algorithm, which is posterior sampling reinforcement learning. So here you have a Bayesian start, you have a prior over the verse, you have a likelihood model, you have a posterior. So these are the words, this is the data, those are the observations. And then you do the following. You repeat the following. It's kind of like similar algorithm. In this case, you're going to sample from the posterior. Okay, so you have possible words, and you have the policies, and you have, actually, this should be the posterior, and so you're sampling from the posterior word. And then once you have the word, you act according to the best policy in that word. And then you go a little wide. It's a little bit unclear, like for how long you should do this. And this algorithm was actually proposed by Thomson in 1933. It was one of the first algorithms ever proposed for bandit problems. And then later on, people find that, wow, this is interesting. Anyway, so the acronym for this algorithm is PS4L. Oh, and the first guy who kind of generalized the idea to reinforcement learning is Malcolm Strauss. That's from 2000, quite a bit later. Anyways, so what happens if you apply these two algorithms to the reverse sim? Well, this is UCR2 regret. Lower values are better. And this is PSRI regret, and this is number of time steps. You can see that like there is a big, big gap between these two algorithms. So how can it be that you have a near optimal algorithm and then you're beating it this much? Well, the question is not entirely answered at the moment, but there are multiple thoughts along the way. So this is very recent. And one thought is that for UCRL and these optimistic algorithms, you have to like do this elimination strategy, and that could be a little bit conservative. So if you can tighten up the elimination strategy, then maybe UCRL2 would be catching up. But we really don't know. So later I'm going to show some other results comparing these two algorithms. Anyway, so this is all great, but this is for toy problems. You have finitely many states and actions, and you're scaling polynomially, and this is not going to solve our AI problems. So we need to scale up. So how are we going to scale up? So need to generalize across states and actions. And today I'd like to talk about the model-based approach. As opposed to a model-free approach. Some people are trying to do that. So in a model-based approach, you simply assume that there is an underlying dynamics to the word. So the state evolves in a certain fashion, and you know this functional relationship. And what you don't know is some parameter in the parameterization of this dynamics. It happens that the finite MDPs that we discussed before can be put into this framework, so they actually do fit nicely. You might think that that's more general, but apparently this framework captures quite a bit. Depends on like how rich is the parameterization, of course. Okay, so but before going big, let's try something small or something classic at least. So one special cases of this problem is a linear quadratic regulation. And whoever knows a little bit about control, this is the first control problem that people learn about. You have a controlled state, you take these actions, that's the next state, and you suffer this cost. These are positive definite. And A and B are the unknown parameters in the learning version of this accurate control problem. And in this case, you have costs, so it doesn't matter. You want to minimize the average cost, so you want to minimize the cost per time step. And the question is, how do you do this in an adaptive fashion? So you can look at the control literature, they have all kind of ideas, but it was actually pretty striking to find out that no one actually proved any regret bound about this system. So once we got these ideas about that you can apply optimism for more general classes of systems. We set out to look into what regret guarantees you can get for this set of systems, and you can prove kind of decent regret bounds. I'm hiding a lot of the details and the constants, but apparently since this is a more general problem than much simpler problems, you can show that this regret bound, at least the way it depends on time, is optimal. So the key idea here is basically to treat this whole problem as a linear estimation problem. You're going to make observations on xt plus 1, xt, and at. You don't know zt plus 1. But you can set up this linear system of equations, and you have the unknown parameters. You have to estimate that. You have some uncertainty around them, and you just have to develop some tight confidence bounds or confidence sets for this setting, and then you can carry through the analysis, and you get this result. So how about nonlinear systems? So this is fine. This addresses a classic problem, but what happens if you have a nonlinear system? So lately we've been working on this, and then you can generalize this result to nonlinear systems. So here I'm going to show a result that concerns not these optimistic algorithms, but became interested in this PSRL algorithm. And so recently we've been able to show some results, regret bounds for PS real for this setting, this smooth setting. So the idea here is that, okay, you have a nonlinearity, but like the next state depends on the nonlinearity in a smooth fashion, where you have a local metric, and the local metric might change, and you have some ideas about that local metric. That's actually pretty important. And you bring in the local metric into the design of the algorithm, and then you can prove this bound. So that's great. But do these algorithms work at all, right? So there's a simple example that's been used in the past. It's that of controlling a web server. So you have two control variables, how long to keep a live connection without traffic on it, and the maximum number of clients that can be served. You have two state variables, the processor load relative to an idealized processor load, and memory usage relative to ideal memory usage. And well, you apply these different algorithms, and let's first talk about what happens with some classic algorithms. So one classic idea would be to explore for a while and then exploit, like for square root t number of time steps. What you see is that, well, the regret, and again, that should be a low number, and this is time, is kind of unhelpful, linearly increasing, and you have a huge variance as well. So these are multiple runs, multiple simulation runs. So what happens to this other algorithm that's also used by DeepMind in some setting with dithering? So again, you see that it has a linear regret. So what happens to this optimistic algorithm is that, like, after a while, it regrets stops increasing, and then you get this nice dependence of the regret on time, this sublinear dependence, and then you can actually improve greatly by allowing an initial random exploration. This is related to that you have no idea about what's the right scale of certain things are, and so if you do some initial exploration, then you can improve greatly further on the results. But so that's fine. So how do these two algorithms, this optimistic algorithm, you can have both algorithms controlling the same system, compare with each other. So we ran some more studies, and so this is the optimistic algorithm, and this is this posterior sampling reinforcement learning. And here, maybe you should concentrate on this green dots. So they show different number of switches, and they roughly correspond to each other. And so you're controlling how often you're switching policies. And what you see is that, well, first, the performance is pretty similar. So maybe this guy has a little bit higher variance. But as you're switching more, so when you're switching more, then you have more computation time. So this is a computation time. The graph is showing a little bit too much, I would say. So when you're switching more often, then you spend more on the computation. When you're switching less often, then you're spending much less on the computation, and this is pretty flat. The other is also pretty flat. So sometimes you can see that switching fewer times is going to hurt you. And yes, like you have initial bad ideas, then you should switch over from, like you should forget those ideas. Sometimes, even if you're switching very often, that's going to hurt you. So there is some sweet spot in the beginning, in the middle. And if you change the system parameters a little bit, you turn up the noise, then you're going to see quite a bit of a difference between the PSRL and the optimistic algorithm. So on the previous figure, the optimistic algorithm was pretty much on par, even possibly better than PSRL. But in this other setting, PSRL is doing better. So and we ran other studies, and we found that it's not entirely clear for these more complicated scenarios which algorithm would be better. Anyways, okay, so that's great. How can we scale up in different ways? So this is another interesting topic, sparsity. Can you bring sparsity to the picture? You're learning parameter vectors, and maybe these parameter vectors are sparse. And from machine learning, we know that when a parameter vector is sparse, then you should learn much faster. So a bandit problem, in case you haven't known, you have a bunch of arms that you can pull, and there are different payoffs that you're going to observe, which are stochastic in this case, and you want to maximize the total reward incurred. It's a reinforcement learning problem where every time step you're finding yourself in the same state. You still want to maximize reward. So the linear bandits is a setting when the actions are embedded in the Euclidean space, and the reward is it's a nicely structured problem. Is the inner product of the action that you choose in an unknown parameter vector contaminated with noise. And the L2 problem, which is like a classic version of this, is when both the parameter vector and the actions are bounded in L2 norm. And for this setting, Donny, Hayes, and Kakady looked into this problem, and they discovered that for the O of U algorithm, they can prove a regret bond that scales linearly with the dimension and with square root of the number of time steps. And they prove a lower bound that's also linear in the dimension. So it seems that in a worst case sense, that's it. You can't do much better. But apparently, so this is one example where you can clearly demonstrate how better confidence sets are going to help you greatly. So just improving the confidence sets in a paper, we were able to bring down the regret of this Donny-Hayes-Kakady algorithm to this level. So it's like, this is almost not growing compared to this guy. This guy is never going to learn. So you can see that like with these optimistic algorithms, it's pretty important to get these confidence sets really tight, like this elimination procedure to eliminate as many words as possible. So what's the challenge? So we have this confidence set design problem. So you have linear estimation problem. You have these observations that take this form, and you want to construct a set in RD such that with high probability the true parameter vector lies in this set. And so the challenge is that the covariates in this case are chosen by an algorithm, and they're highly dependent. It's not like that you would be independent inputs. These inputs are not independent. And also we need an honest confidence that it's not just an asymptotically correct confidence set, because then the algorithm would break down. And on the top of it, so right now we'd like to exploit the sparsity of a parameter vector. So the question is, how can you do that? And so we came up with a solution a little while ago. And the core idea is that if you have a good predictor for an adversarial linear regression problem, and such that that predictor has a small regret, then you can use the predictions of this predictor together with the regret bound to construct a confidence set. So the confidence set might look a little bit unwieldy to you, but it's actually, the idea is pretty simple. So these are the predictions of an algorithm that is tailored to a situation like sparse problems, right? So it's gonna do things differently than if it didn't know that the parameter vector was sparse. The predictions are going to be tailored to that, and they're expected to be pretty precise, okay, because the algorithm's clever about sparsity. So you take a look at this quadratic expression here, and you can expand this in terms of using, like you can plug in back the observations, and you can do some linear algebra, and some martingales are going to appear, and then you reorder things. And then it's like a two-line proof to prove that this is indeed a confidence set. So although it looks a little bit unwieldy, it's actually not that difficult to do this. So great. So we can have like all kind of situations for which you can design perhaps really tight confidence sets. So the first thing that we wanted to do is this, of course, to address the sparse bandit problem. So you have a bandit problem where the parameter vector is sparse. You have this general umbrella theorem that you bring this to the bandit setting, then what you're going to see is that the regret scales with square root dimension times t times the regret bound for the adversarial prediction algorithm. And you put this together with an algorithm that achieves a good regret, and such an algorithm was, lucky for us, proven to exist by Gerchinowicz in 2011. You put these two things together, and voila, you get a regret bound that scales like this. So the question is this good enough? Did we win? Because we started off with an expression that involved, if you remember, it was linear in D. So right now we still see D, the dimension in the expression. So it's kind of like worrisome that the dimension didn't appear. It didn't just go into a log factor like that. So in a prediction problem, you typically see the dimension appearing only logarithmically. And in this bandit problem, the dimension is still there. So is there something wrong with our technique? Well, unfortunately, you can say that no. So you can prove a lower bound that says that for sparse linear bandit problems, the dimension is never going to go away. It's going to be there. Okay, so this is a worst case result. So some caveat here, right? So it's a worst case result for all sparse problems. And in these worst case results, of course, you're selecting everything to the horizon. And so maybe there is some room for improvement, but not in a worst case sense. Okay, so why is this happening? So as I said, for prediction problems, you have this nicer looking bound. So what's the difference? So I thought a lot about it. And what I think is that the problem is that the good algorithms are going to select the good actions very frequently. And so the conditions under which you have these much nicer results hold under a condition that is going to be violated. So this maybe is not going to happen, like not in this sense, not in this way. Well, that's great, but you might ask whether this was worth the effort. And here I'm just showing on a 100-dimensional problem with a sparsity of 10 that, yes, it was well worth doing. You see two algorithms here. So one is based on a least squares approach. It doesn't exploit sparsity. That's the best algorithm that was beating the old algorithm by that huge margin. So that's the best algorithm that we have for the general case. And here is the algorithm that is exploiting sparsity. So indeed, you can say that it was probably still worth the effort. So it's not so bad. All right, so with that, I'd like to summarize. So maybe the most important message of the talk is that we need to solve decision problems. And this is going to make a big difference. So it's not just like you have to learn about making predictions. If you want to act on the information that you have, then there could be huge challenges down the road. And I was talking about one of the challenges, which is that passive data collection can be extremely ineffective. You're never going to see big data for certain problems. So you have to be smart about how you're going to collect data. So if you're doing this learning by controlling and you want to get good performance along the way, then planning to learn is critical. So today I talked about two general principles to design these algorithms. And I was comparing them, and at the moment it seems that practically on a bunch of examples, PSRL is winning, but it has its own limitations. You need a likelihood model for the observation, so it's model-based, and if it's UFO, you can make it model-free, so it's not entirely clear where this is going to go up. But current research is about scaling up. We talked a little bit about sparsity. but a lot of other things remain to be done. So I'm really delighted to be around this time of doing research in machine learning because a lot of things are happening, but at the same time you can see that the road to get there is maybe going to be a curvy one, maybe it's going to have a few bumps here and there, but I hope that we're going to get there. Thanks.
It's open for question.
Yeah.
Do you have any comments on the evaluation of different different? So how do you evaluate the different policies in terms of what actual problems you test them on? Just because different problems have very different characteristics.
Right.
And so when you show these graphs, that might be for one class of problem.
Right.
In terms of their performance, but
right. Right. So you might not be able to generalize from a few graphs that you're showing. So one good answer to that is that people are starting to take this very seriously. So this Ottery game domain was picked because it's a huge number of very diverse set of games. And the belief is that if you have an algorithm that is able to perform well across that many domains, handle that diversity, then it's going to work well. At the same time, many times when you're doing a study, then you're doing the study because you want to delve deeper into understanding your algorithm. So these studies are more geared towards that. But if you want to evaluate your algorithms, then you should absolutely pick something broad. And yeah. Yeah?
Slides behind.
Go back a few slides?
Yeah. Yeah, this one.
Okay.
Next one.
Yeah.
Yeah. So, how are the regret bounds depending on the sparsity? Here you have like e equals 10, and if you observe something, e equals 2.
Right, so the scaling with p you won't see from this graph, obviously, because it's plotted against time. And I guess you're asking whether, like, in actuality, like, if you would be, like, plotting the graph against p and you would keep everything as the same. We haven't done that, but we do have some lower bounds that say that it should be square root dp. Yeah. But, so the hope here that I alluded on a little bit is that like the results I presented are pessimistic worst case results. And there could be subclasses of problems for which you could see much better performance. So, and also if you look at like an asymptotic type of result, then you might be able to get rid of the D dependence. But it's not the dependence on p that worries me. I think the dependence on p is fine, like square root p, fine. The dependence on the dimension, that's bad.
Do you think that once we have like very sparse matrices, that your regret bounds are going to not be dependent on D but on P? In a sense.
No. Actually, if you push sparsity to the extreme, you have one parameter vector. One parameter, so the parameter has one entry that's non-zero, all the others are entry, the lower bound holds. Yeah. Yes.
So your kind of example of a swimming lesson made me think about obviously the possibility of providing feedback to the agent, not just in terms of reward, but maybe in terms of that would have been a better action or a sequence of actions.
Giving advice, you mean?
Yeah, some kind of feedback that is more
Right.
complex or more structured than.
Right. Actually,
So I was wondering if everything you have said is just limited to the fact that the feedback has to be a reward for
Well, there is more feedback in the sense that you're going to have some observations. So in the reverse swim problem, you're going to see whether you actually made it to the next state or not, right?
That's just your
And
knowledge about the...
but it's not a richer set of rewards that, like, you could imagine that you're trying to teach a robot, right? And then you see that the robot's doing something wrong, then you would like, stop it there, do this differently, right? So we didn't investigate anything like that. There are people interested in this like joint learning when there is a human interacting with an agent, but that can tremendously speed up learning. Of course, the humans always represent the bottleneck at the same time. So at the same time, it's advantageous to think about just the pure setting where there's no human in the loop, right? So if you have to babysit your robot.
Yeah, I was thinking maybe it's not a human, it's another system.
Oh, another system. So richer observations, it's totally part of the picture, actually. I'm working on a problem setting where you have rich set of observations, and it's like a generalization of bandits. So instead of observing your reward, you just observe some other things that may be correlated with the reward, or can be, or they can give you more information or less information. It's a very interesting set of problems. Yes.
What are some of the assumptions that can get you from square root of t down to log t?
Oh, so when you see this, okay. You're talking about bandit problems, or like we have to be more specific, because I mean, in general, you could say that some kind of curvature, like, optimization will bring you down. But in these settings, often even the worst case results are going to be square root t. But these are worst case results. But at the same time, in the bandit literature, you're going to see the log t bonds. The log t bonds have a different nature. They're asymptotic bonds. They say that asymptotically, the growth rate of regret is not more than that. I mean, like, asymptotic, it's a problem. Okay, so I shouldn't say asymptotic. I should say problem dependent. So these are problem-independent bonds, worst case within the class of problems, and then you choose the worst problem for a certain horizon, and you see the square root t popping up. Or you can be problem-dependent, and when you prove a problem-dependent bond, then you see all kind of problem-dependent constants appearing, and then some people would shy away from that because, wow, it's creepy. Then you try to prove a lower bond, but proving problem-dependent lower bonds, there are very few techniques that we can do. Like, you can prove asymptotic problem-dependent lower bonds. Asymptotically, you might be able to match. Because you always want to know whether your algorithm is doing the best possible, right?
I mean, don't you want to try and characterize what the easier problems are?
Yes, you do. Absolutely. Yes, you want to characterize, yeah, that's part of the game. You can do that both in a problem. The problem-dependent bonds, whether that's a characterization or not, it's a question. It's a characterization in a certain sense, in an asymptotic sense. So when you fix a certain parameter, then proving a lower bond in a non-asymptotic, like, you have to scale something in order to be able to prove a lower bond, right? You have to have some alternatives, and then in that case, you scale the time, right? Because you can't play around with the problem parameters, because those are fixed. So there are these two types of results, and maybe there are things in between, but that's not very well understood. Yeah.
So I was wondering if you could comment on if you're interested in trying the outcomes of this research in specific application domains where decision making is important and can
Right.
make a difference in the real world.
Okay, I actually do work with some guys in the industry, and we are trying to apply these results in the industry. one of the challenges that is a tremendous challenge is to convince the managers that they should allow the machine to learn online and try things, explore things that it hasn't tried, right? So there is a tremendous resistance from, people are conservative, like, what's going to happen to my beloved system if I just let this machine learning algorithm to make the decisions on the fly, and I didn't test it offline and a huge amount of data. And these examples actually show you that you might be missing out by a big margin if you never let the machines to do the data collection on their own. And so that's a big fight with managers in a company. So what you can actually do is that you can kind of approximate this setting, and maybe you change a little bit the objectives, so you have to kind of stay close to known regions of the state space where people are comfortable, and then like if you work very hard, then you can convince people to use these algorithms on the fly. So yeah, it's pretty challenging to convince people, but I think that it's a big mistake not to do it. Like eventually it's going to backfire, and there could be some problems where you're never going to discover that you had a solution in front of your eyes, you just never tried it. Right?
Yeah, do you have any ideas on how to win this battle and convince them?
How to win? Like, you have to be persistent and maybe come up with good examples where they could be missing out. Yes. I think there is a progress though. So a lot of the companies that do this online data collection on the web, they're experimenting right now, as of we speak, with algorithms that are allowed to change things on the fly. But so once someone takes the first steps, the others are going to follow, right? It's very hard to be the first.
Any more questions?
I have seen some benchmarking contextual planting from Yale, and I'm wondering if your approach in this data set, what's the evaluation? I mean, is it better than -CB or?
Oh, yeah. So LinUCB would be another algorithm to try, and it all depends on. So I think that the awful algorithm is going to be competitive with LinUCB. Some people tried it, and it seems to be competitive. The big difference between LinUCB and this algorithm is that this algorithm actually does have a guarantee, whereas LinUCB doesn't. LinUCB is a nice hack. It's a beautiful hack, but no one can prove that it works.
There is proof of work at all.
Oh, well, there are some papers that are not entirely correct out there in the literature.
Okay.
Yes.
How about the contextual Thomson sampling?
Pardon? Well, the Thomson sampling is like the PSRL, what I was talking about. Yes.
I mean, the contextual version.
Right.
From. Have you compared that?
Well, we didn't compare to that. Like, those are newer. Yeah.
Great. Let's thank our speaker.
They have high stakes. Yeah.
Yeah. Yes, government agencies, but they have their own agencies as well.
I mean, on the story domains, then of course there is nothing much to lose. So we are talking with DeepMind, and they are going to do smart exploration, like their learning algorithms too. So that's really obviously they have to do that, because if you look at what type of games they announced, companies are taking that I use.
Yeah.
If you don't do some explanation, the reward, if you never see the reward, then you know how to have it.
Yeah. Like games is where there's no action.
I mean, so they use their games as a test, right? A proof of concept, and like, who knows what they're going to do.
Yeah.
Thank you very much. I appreciate it. So,
You'll have a. Yeah, you can go ahead. You can do that later.
My name is Jeremy.
Yeah, keep taking the what is it? 3:15. Yeah.
And there's a taxi, his name is Csaba.
Yeah, thanks. So just mall when you get right on the corner. Yeah, okay, cool, great, yeah.
Thank you. Last year we had developed
Yeah.
algorithm-based neural networks.
Thank you.
thanks for
Yeah.
the invitation.
Yeah, I got some.